Hi, I'm Aditya and I'll be presenting our work titled Simple Unsupervised Knowledge Distillation with Space Similarity. This study was performed in collaboration with Professor Haohan Wang. Knowledge distillation is a widely known training technique where we train a smaller model using signals from a larger model. The smaller model is called as the student, whereas the larger network is referred to as the teacher. In unsupervised knowledge distillation, we do not have access to the target labels while training the teacher and training the student. Recently, it was observed that many self-supervised learning approaches do not readily extend to smaller architectures. As a workaround, unsupervised knowledge distillation was applied to train a well-performing smaller network. A common pipeline for unsupervised knowledge distillation is to pass an input image through the teacher and the student networks, then gather the latent features from both these models. Often, an embedding queue is also used, which keeps a record of features generated by previously seen input samples. This embedding queue is used to manipulate the embeddings of the input, and the final vectors thus obtained are aligned using some loss function. This pathway is followed by many existing approaches. We discuss them in detail in our paper. The motivation for our work stems from the fact that feature normalization such as L2, which is applied by all approaches, leads to loss of some information. For example, if we imagine an embedding space of the teacher, where an image of an airplane, car, and a truck all fall on a straight line, L2 normalization will map them to a single point on the unit hypersphere. This can potentially lead to loss of teacher's manifold structure, which we hypothesize as its knowledge base. As a solution, we propose a simple objective to account for teacher's latent space information. Alongside the well-known objective of feature similarity, which is applied to the corresponding pair of latent embeddings produced by the same input, we also maximize the similarity of corresponding feature dimensions within a batch. With the toy experiment, we demonstrate that capturing space similarity allows the student to mimic its teacher's embedding manifold. We show this for two different datasets, half-moons and circles. First, we train a simple MLP on these datasets and visualize their embedding spaces. We can note distinct structures present in them. For existing methods which do not explicitly capture the space similarity, latent space of the students is very different compared to the teacher. However, using the space similarity objective, we are able to capture the finer details of the teacher's embedding manifold. We show that adding the space similarity objective also improves the performance of the student on many real-world cases. Here we assess the performance on ImageNet 1K dataset. The teacher is trained using self-supervision, and applying the same SSL technique to a smaller network leads to a large drop in performance. However, a student distilled with space similarity is able to narrow down this gap in performance. We also report results on transfer learning, object detection, image retrieval, and several other benchmarks in our paper. To conclude, similarity objective is simple in implementation but provides substantial benefits for unsupervised distillation. Thank you.